one by one. If you are differentiating this one, they will be easier than this. So if you know how to use partial fraction and then you know how to use this one, but I guess this one is faster because you first go into process of partial fraction before you come to this end. So whichever way you feel you understand, you can do it like that. So f of 3 or f of 3 is 1. F of 3 equals to 1. F prime at 3. F prime at 3 is minus 3 of z minus 3 plus f prime prime of 3. So f prime prime of 3 is this 7 over 2. 7 over 2 times z minus 3 all squared divided by 2 factorial and on like that. So this is 1 minus 3 into z minus 3. If you want to open the bracket, plus 7 over 2 factorial, that's 7 over 4 z minus 3 all squared and on like that. So this is z. So that is basically how to use Taylor series to expand a complex function at a particular point z. Now let's move to the other series, Laurent series. Now Laurent series. Now, so this Laurent series now is just like we are expanding two functions at a time. So at a different region. Now, if I have something like this, let me start from, look at this inequality. Absolute value of z is greater than 1. So this is z is greater than 1. If z is greater than 1, it means that 1 is less than z. If z is greater than 1, it simply means 1 is less than x. 1 is less than z. If I have, let's say I have 1 is less than z, z is less than 3. What does it mean? So 1 is less than z. It means that if I'm going to region 1, z will be what? It's greater than 1. So this one is like z is greater than 1. Z is definitely greater than 1. And if I'm moving like this, z is less than 3. So this is 3. Z is less than 3. That's 3 is greater than z. So this is the interpretation of these two inequalities. So if I have 1 less than z less than 3, it means z is greater than 1 and 3 is greater than z. Okay, so and then from the beginning of the video, we've highlighted some useful series. First, 1 over 1 minus z. The second is 1 over 1 plus z, and on like that. Now, the Laurent series consists of two parts. Now, we need to ask ourselves, why are we learning this Laurent series and Taylor series? So the reason why we are learning it is that when we get to the other part of this course, calculus of residue. So if I want to, let's say I want to evaluate e raised power z over z minus 1 raised power 5, for example. So if I want to do something like this, so I will need to go and expand some function. I will need to go and expand z minus 1 all raised power 5. So with the aid of my Laurent and Taylor series. So we basically need this Laurent series where we get to application of residue and residue theorem. So that is the purpose of this Laurent and Taylor series. So it consists of two parts. Number one is the analytic part. The analytic part, and we also have the co-analytic part. Co-analytic part. So how does it look like? It's like f of z equals to summation ak z minus z naught all raised power k. That one k starts from 0, end at infinity, plus summation k now start from 1 and end at infinity, b divided by z minus z naught raised to power k. So this part where k starts from 0 and ak is multiplying z minus z naught is the analytic part. This is the analytic part. And then the other one here is the co-analytic part. So our expansion will definitely be in two forms. One, a function will multiply z minus z naught. Don't forget, z minus z naught is the region where we are taking our expansion. So the other one, a function will divide by z minus z naught. So let's discuss what is called region of validity now. Region of validity. Region of validity of complex variables. Now don't forget, during our video on analytic function, we said that a function will stop being analytic. Let's say we are having f of z equals to 1 over z minus 1, z minus 2. This function will be analytic except at 2 points, except when z is 1 and when z equals to 2. At these 2 points, this function will stop being analytic. At a point whereby a function stops being analytic is called the singular point. So if I want to find the region of validity of any complex variable, just take the denominator and then we equate it to 0. So let's say we're having f of z equals to 1 over 1 minus z, 2 minus z. So let's discuss the region of validity of that function z. So to get the region of validity of this function, now it means that there will be a particular point whereby this function will stop being analytic. They are basically asking us to find the singular point of this function z. So if I have 1 over 1 minus z and 2 minus z now, I will just say that, oh, 1 minus z and 2 minus z, their region of validity will be at a point whereby these two functions is what? Is less than 0. Sorry, it's greater than 0, sorry. So when 1 minus z, 2 minus z is greater than 0, what does it mean? Either 1 minus z is greater than 0 or 2 minus z is greater than 0. 2 minus z. So if 1 minus z is greater than 0, it means that 1 is greater than z or 2 is greater than z. So that is the region of validity of this function. Whenever you are asked to get the region of validity, just take the function less than 0. Now let's now move to Laurent series. Don't forget that it's actually divided into two parts, analytic and co-analytic parts. So let's start. Let's expand f of z equals to z over z minus 1, z minus 2. At this point, 1 is less than absolute value of z less than 2. So this is where we want to expand. So you see the difference between Taylor and Laurent series. In Taylor series, they will ask us to expand at a particular point. So here now for Laurent series, we want to expand at these 2 points, at 1 minus z and 2 minus z. So the first thing is that we will first break this one down into partial fraction. Yeah, this is z. Huh? Which one? This one. We just want to discuss the region of validity of this one. So f of z equals to z over z minus 1, z minus 2. So I want to expand this. So the first thing is that we resolve this thing into partial fraction. Solution. So resolve into partial fraction. Well, I won't do that one for us again. I believe partial fraction is not something that is difficult to do. So if I want to resolve z over z minus 1, z minus 2 into partial fraction, I'll just write the solution. You say a over z minus 1 and b over z minus 2. So you do your necessary estimation and get a and b. We resolve into partial fraction, we are going to have z over z minus 1, z minus 2. It will equals to minus 1 over z minus 1 plus 2 divided by z minus 2. This is the partial fraction. So don't forget, we are expanding at where 1 is less than absolute value of z and that z is less than 2. Now, for the first fraction, this is minus 1 over z minus 1. So this one will go for it. For the second fraction, 2 over z minus 2, this one will go for it. Now, the meaning of this is that 1 is less than z. It means z is greater than 1. So under this, z will be greater than 1. Z will be our common factor. So that is, we are going to have minus 1 over, we take the z, we take it out. Z into bracket, this is 1 minus 1 over z, right? Because z is bigger here. So we take the bigger one out. Plus 2 over, in the other one, z is what? Is less than 2. If z is less than 2, it means 2 is greater than z. From here now, the bigger one, 2, is what is going to be our common factor. So 2 over z minus 2 now. This minus 2 is what I'm going to bring out into brackets. If I bring minus 2 out, this one will be minus, this will be 1, or plus, I have z here. This will be z over 2, right? Or minus 2 times 1, minus 2. Minus 2, oh, sorry, this will be minus as well. So minus 2 times minus z over 2, it will be plus z. Again, whenever you are having a function like this, you first break it down into partial fraction. Then this region of expansion is what you just need to check. In the first one, we have z minus 1. The first one here is 1 less than z. It means that z is greater than 1. From here now, z is the common factor. Z into bracket 1 over 1 minus z. Assuming you are having something like this now, you are having z is less than 1. For example, sorry, let's say you're having z is less than 1 alone. Let's say you're having z equals z is less than 1 alone. Now, if z is less than 1, it means that what? 1 is greater than z. From here now, 1 is going to be our common factor. It will now be 1 minus 1 over z. Sorry, 1 minus z. So this is how it's going to be if it is like this. Because z is less than 1, it means that that one will be greater than z. That one that is greater is what you are going to write out as your common factor. So if you're having something like, oh, absolute value of z is less than 2. If z is less than 2, it means that 2 is greater than z. Here now, you take 2 out, fine. If 2 is greater than z, well, 1, 2 will be greater than z. 1 is what you are going to take out. So we just need to check this region of validity. So we're having z into bracket 1 over z and 2 over 2 into bracket 1 over z minus 2. And don't forget, we've already established that whenever we're having something like 1 minus z raised to power minus 1, it will be 1 plus z squared, and on like that. So we're having minus 1 over z into bracket. If I raise these two up, it will be 1 minus 1 over z raised to power minus 1, right? 2 cancel 2. Plus times minus minus. If I raise this one up, it will be 1 minus z over 2 raised to power minus 1. So if I expand this, this will be minus 1 over z into bracket 1. You know, if you're having something like this, 1 minus z. So this one will just be plus plus plus. So this will be 1 plus 1 over z plus 1 over z squared plus 1 over z cubed, and so on like that. Minus 1 minus z over 2 all squared. That one too will be 1 plus z over 2 plus z squared over 2 squared plus z cubed over 2 raised to power 3, and so on like that. So we are done with our expansion. Okay, open the bracket here with minus 1 over z. If I open the bracket with minus 1 over z, this will be minus 1 over z, minus 1 times this, minus 1 over z squared, minus 1 over z cubed, minus 1 over z raised to power 4, plus dot dot dot, minus. So open the bracket. If I open this one, this will be minus 1, minus z over 2, minus z squared over 2 squared, minus z cubed over 2 cubed over 2 cubed, and so on. So collect like term. This is is there any likely term here that we can? No. So there's no like term. So we can actually generalize this. So if I generalize it, this will be summation z raised to power 1, z raised to power 2, z raised to power 3. This is z raised to power n, right? Minus minus minus. So well, that's minus 1 over z raised to power n. N starts from where now? Starts from 1, goes to infinity. Plus this one, 2 square, 2 raised to power 3. This is like 2 raised to power 0. Let me say this one starts from 2 raised to power 0, 2 raised to power 1, 2 raised to power 2. This is 2 raised to power n. 1 z square, z cube. Oh, this is z raised to power n, right? But everything here is minus. Well, let's don't worry, let's put plus, and then we're having our plus here. So this one will be minus, will be here now. Minus will be here. This minus. This is minus. So this will be z raised to power n divided by 2 raised to power n, right? So here n starts from where? N starts from 0 and goes to infinity, and that's our Laurent series. One is analytic, the other one is co-analytic. The one that starts from 0, the one that starts from 0 and goes to infinity, that's the analytic part. This one is the analytic part. The one that starts from 1 and goes to infinity is the co-analytic part. So that is how we use our Laurent series. That's one example. Number 2. So let's expand by Laurent series. Z divided by z squared. Z divided by z squared minus 3z plus 2. At this point, absolute value of z plus 1, this. So absolute value of z plus 1 greater than 1. Look at this function. So the first thing is to break this one down into partial fraction. So we're having our f of z is z over partial fraction. Now we factorize this. This is z minus 1. And then, sorry, this is z minus 1. This is z minus 1 and then z minus 2. So that's, if you resolve it into partial fraction, you are going to get minus 1 over z minus 1 plus 2 divided by z minus 2. Now, after doing that, we want to expand at absolute value of z minus 1 greater than 1. Fine. So here now, we've already had z minus 1. So it will be minus 1 over z minus 1, where this is greater than 1, plus the other part here, this is z minus 2. The thing is that we must express this denominator 2 in terms of z minus 1. So this will be plus 2 over z minus 1 minus 1. This is this z minus 2. Z minus 1 minus 1. So what does this thing mean? It means that z minus 1 is greater than 1. It means that 1 is less than z minus 1. So if 1 is less than z minus 1, this z minus 1 will be our common factor. Okay, so here is just z minus 1. So nothing. So this is a minus 1 over z minus 1 plus, here now our common factor will be this z minus 1 is greater than 1, is greater than this 1. So we are going to have z minus 1 into bracket 1 minus 1 over z minus 1. That will be our common factor. Then we expand this. So if we are having that, this is 1 over z minus 1. You can say this is 1 over z into 1 minus 1 over z plus 2 over z minus 1 into 1 minus 1 over z minus 1. Raise this one up. Minus is here. This will be minus 1 over z into 1 minus 1 over z raised by minus 1 plus 2 divided by z minus 1 into bracket 1 minus 1 over z minus 1, all raised by minus 1 as well. So in that case, this is minus 1 over z into bracket 1. Don't forget our series. This will be 1 over z plus 1 over z squared and not like that. This is plus 2 over z minus 1, 1 plus 1 over z minus 1 plus 1 over z minus 1 all squared and on. So if I use z to open the bracket here, this is minus 1 over z plus 1 over z squared plus 1 over z cubed and so on. And if I use z minus 1 to open the bracket, 2 1 over z minus 1, 1 over z minus 1 all squared, 1 over z minus 1 all cubed and so on like that. So if we generate the nth term of this one, so this is minus summation 1 over z raised to power n. Z starts from where? Z starts from 1 going to infinity plus summation. Yeah, this is 1 over z minus 1. Z minus 1 starts from 1, and that is 1 over z minus 1. That starts from 1 and end at n. So 1 over z minus 1 raised to power n. So all this one I just start from 1 and end at infinity. Start from 1, also end at infinity. So that is all. the expansion of 1 over z over z square minus 3z plus 2. The first thing is that you check your partial fraction, and then region, at the region we are given to expand will determine which one are we going to take up, which one is going to be our common factor. So let's try another one. So let's expand by Laurent series. Expand 1 over z square plus 1 and z plus 2. At which region? At 1 less than z less than 2. That's one problem. And then I think that's the only one. So if I want to expand this stuff now at this region, what's the first thing? I'll first break this one down into partial fraction. Don't forget, what type of partial fraction is this? Denominator with non-factorizable quadratic factor. So if you want to do the partial fraction, let's say we are having ax plus, is it az this time around, az plus b over z square plus 1, and the other one will be c over z plus 2. Then you solve the partial fraction for a, b, c. So viewers, so I'll leave that one for you. So the partial fraction here is that minus 1 over 5 multiplied by z minus 2 all over z square plus 1 plus 1 over 5 1 over z plus 2. So this is my, I've solved it before the class. So from there now, we've gotten our partial fraction. Then the next thing is to use this region of validity now. This is 1 less than z. If 1 is less than z, it means z is what? Z is bigger than 1. If z is bigger than 1, so from here, this z is bigger than 1. If I want to expand this side now, 1 is less than z. It means z is bigger than 1. This z that is bigger will be my common factor. In the other part, z is less than 2. It means that 2 is bigger than z. This 2 will be my common factor here. Simple. So it will now be minus 1 over 5 z minus 2 over, factorize this. If I take z square out, we are going to have 1 plus 1 over z squared. Okay? Plus 1 over 5 times 1 over, here z is less than 2. It means that 2 is greater than z. 2 plus 1 over z over 2. Isn't it? Yes, so 2 times 1, 2 times z over 2. So take this one up. So we are going to have minus 1 over 5z squared times z minus 2 into 1 plus 1 over z squared raised to power minus 1. This is 1 over 10. This is 1 over 10. 1 plus z over 2, that one to raise power minus 1. Okay? So expand this. Don't forget our special series. If it is plus, it will be alternating. If it is minus, everything will be plus. So this is minus 1 over 5z squared times z minus 2 into bracket. This is 1. The next one will be minus 1 over z squared. The next one will be plus. Plus 1 over z raised power 4, because we are squaring them. The next one will be minus 1 over z raised to power square 6, and so on like that for this one. Then the other part, 1 over 10 into bracket 1 minus z over 2 plus z square over 2 squared minus z raised to power 3 over 3 squared, and so on like that. So the next thing is that open the bracket with z minus 2. How do I do that? Wow. If I want to open the bracket with z, should I start from here or I should use this one first? Anyhow. So this is minus 1 over 5z squared. Use z to open the bracket. That will be z. If I multiply this one by z, one z will go. We are going to have one here. Multiply this one by z, 1 over z raised to power 3. Multiply this one by z, 1 over z raised to power 5. So on like that. Then multiply by 2. 2 times 1 minus 2. 2 times this. That's plus 2 over z squared plus 2, minus 2 over z raised to power 4 plus 2 divided by z raised to power 6, and so on like that. So nothing here. This is plus 1 over 10 into 1 minus z over 2 plus z squared over 4, and on. Then collect like term. Is there any like term? No like term. So open the bracket again with over z squared. So if I open the bracket with divided by z squared, So if I open this bracket, well, everything here, is there any like term that we can basically whether add or subtract? No, this is z squared. They do not have anything in common. So open the bracket with divided by z squared. Well, I'm going to have minus 1 over 5 outside, divided by z squared times z. That will be 1 over z. Divided by z squared times 1 over z. That's 1 over z raised to power 3. This times this, 1 over z raised to power 5. This times this, 1 over z raised to power 7. And so on like that. Divided by z squared times minus 2. That's minus 2 divided by z squared. Divided by z squared times 2 over z squared. That's plus 2 divided by z raised to power 4. Divided by z squared times 2 over z4. Minus 2 divided by z raised to power 5. And then plus 2 divided by z raised to power 7. So that one end. And this, we're having plus 1 over 10 into 1 minus z over 2 plus z squared over 4 minus z raised to power 3 over 6. So that will be my Laurent series. If you want to generalize, well, you can generalize this as 1 over z raised to power n. So yes. Well, if I want to generalize this, let's do it. This is minus 1 over 5 summation 1 over, this is 1, 3, 5, 7, odd power. And every odd can be expressed as 2n plus 1, right? So this is 1 over z raised to power 2n plus 1. Is it alternating? Yes, it's alternating. If it is alternating, I have to put minus 1 raised to power n here. Where my n starts from where? It starts from 1, goes to infinity. That is the general term of this one, of this odd part of it. Why z raised to power 2n plus 1 is because this power here is odd. 1, 3, 5, 7, 9. If you want to know, go back to your AP. Tn equals to a plus n minus 1d. If you're having 1, 3, 5, try to get the nth term of it. That's 1 plus 1, 2 minus 1 times 1. That's 1 plus 2n minus minus 2. So you get 2n minus 1 as your 2n minus 1 as your nth term for this one. And then don't forget, minus 1 over 5 is still multiplying this summation. This is a 2, 2, 2, 2, 2, 2. So this is 2 over z square. This one starts from z square, z4, z5, z7. So z raised to power what? You're having 2, 4, 5, 7. Get the nth term of this. N starts from 1, goes to infinity. Is it alternating? If it is alternating, you put minus 1 times 2. So that's the co-analytic part. The analytic part now, we're having plus 1 over 10 summation 1 z square, z raised to power 3. This will be z raised to power n 2, 4, 6. If it is 2, 4, 6, is it 2, 4, 6? Yes. Sorry. It is 2 raised to power 3 or 2 raised to power, sorry. Okay, z over 2 or raised to power minus 1. So that's a 2 square. It is a 2 square. This will be 8. That's 2 raised to power 3. The next one will be 2 raised to power 4, 16. So summation z raised to power n divided by 2 raised to power n. Now check, is it alternating? Plus, minus, plus, minus, plus. So you put minus 1 all raised to power n times z raised to power n. Our n starts from where? N starts from 0. Because this one starts from 0. Goes to where? Goes to infinity. So that is the Laurent series of that expansion. So the last part of this expansion is if f of z has a pole at z. This is just like the special case of this expansion. If f of z has a pole at, let's say, z equals to a, what is the purpose of that one? Now, suppose we are asked to expand by Laurent series. We are asked to expand, yes, P-A-N-D. We are asked to expand f of z equals to e raised to power z divided by z minus 1. All raised to power what? Give it any power other than power 1. Let's say all raised to power 4. We want to expand e raised to power z over z minus 1 at where? At z equals to 1. We want to expand using Laurent series. You know, if you see something like this, you can say, oh, I'll use Taylor series because they are being specific. At z equals to 1, I'll take f of 1, differentiate, put 1. But here we want to use Laurent series to expand this function at this 1. So that is all what we are going to talk about now. Michelle Tom, viewers let my ship for you. So e raised power z divided by z minus 1 raised power 4. So this is a special case of Laurent series. So if you remember from the beginning, I said the purpose of learning this Laurent series is to integrate some improper function. Now suppose this is not expansion, they put integration like this, let's say from 0 to 2 pi, for example, or whatever. So what we are just going to do is that we take the Laurent series of this, then we take the second term, the one with 1 over t, and then that's all. Though when we get there, we are going to talk about application of this Laurent series in residue. Now, here we are going to say this is z minus 1. We want to expand. You know, if I equate this one to 0, this function will stop being analytic at z equals to 1. And then we want to take the expansion at z equals to 1. We now said, let this z minus 1, let's call it, let's say t. Let z minus 1 equals to t. You know, collect like term, z will be what? T plus 1. So the function will now be f of t plus 1 instead of f of z. So f of t plus 1 will now be e raised to power z. That's e raised to power t plus 1 divided by z minus 1. That's t raised to power 4. So with our indices, we can break this one down to e raised to power t times e divided by t raised to power 4. Right? And e is a constant, so it doesn't have any effect on our expansion. We are going to have e multiplying e raised to power t divided by t raised to power 4 divided by t raised to power 4. Right? And from our special series, we know the series of exponential z, e raised to power z equals to 1 plus z squared. So this one will just be e times, just expand this. If I expand this, I'm going to have 1 plus z, 1 plus t plus t squared divided by 2 factorial plus 3 raised to power 3 divided by 3 factorial, and so on like that. Dividing by what? Dividing by t raised to power 4. So that's e over, divide this one by t raised to power 4, 1 over t raised to power 4. Divide this one by t raised to power 4, 1 over t raised to power 3. Divide this one by t raised to power 4, 1 over 2t squared, right? Divide this one by t raised to power 4, that's 1 over 3 factorial t. Let me just say 3 factorial t. And so on like that. And that's all. That is all. So if I get, that's my expansion. Going back to t equals to what? T equals to z minus 1. So our expansion is just e into brackets 1 over z minus 1 raised to power 4 plus 1 over z minus 1 raised to power 3 plus 1 over 2 z minus 1 raised to power 2 plus 1 over 3 factorial z minus 1, and so on like that. You can generalize. If I want to generalize this z minus 1, well, let's disturb ourselves. This is e times summation 1. Is it alternating or not? No, it's plus 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 divided by, now this series starts from 4 power 4. Let me first put z minus 1 because z minus 1 is common. Raised power 4, raised power 3, 2, 1. If I have a sequence 4, 3, 2, 1, if I want to get the nth term, let's say my a is 4, right? My d is 3 minus 4, d is minus 1. So Tn equals to 4 plus n minus 1. N minus 1 times minus 1. So this is 4 minus 4n plus 4. 4 cancel 4. No. 4 plus 4, that's 8 minus 4n. Right? That is it now. Is it 4? Yeah. This is 8 minus 4n. Is it 4? 4 plus n minus 1 d. D is 3 minus 4. That's 4 minus 4n. Oh, plus 1. Yeah, thank you. So 4 plus 1 is 5, right? It's 4 minus n. Oh, 4 minus n plus 1. Thank you. That's 5 minus n. So this is the series will just be 5 minus n. N starts from where? If n is 1. Oh, n start from 1 and think goes to negative infinity because it's going down. So what other thing? This is a 0 factorial. That's 1. 0 factorial. So this is like 0 factorial, 1 factorial, 2 factorial, 3 factorial. N factorial will be here because this is 0 factorial, 1 factorial, 2 factorial, 3 factorial. So that's all. Oh, n starts from 1. If n is 1, 1 factorial is still 1 and 0 factorial is 1. If n is 2, oh, n starts from 0. Let's say n start from 0. 5 minus 0. If n is 1, should I put it in sum? Or this is divide, this will be diverging series. So doesn't it? That is it. So if you see e raised power 2z, you should know how to play with it. That would just be e raised power z square. So that is when that function has a pole at z equals to a. So the last example on that. So this will be our f of z now. So the last example. Okay. So let's get the Taylor series of 1 over z and z plus 2 raised by 3 at z equals to minus 2. Expand. F of z equals to 1 over z plus 2 all raised by 3 at z equals to minus 2. So you know that this function will stop being analytic when this thing is 0. That is when z is minus 2 or when z gongon is 0. So we say that, oh, let z plus 2, let's call it t as usual. If z plus 2 equals to t, what does it mean? It means that z is equals to t minus 2. Then we are expanding f of z. F of z will now be f of t minus 2 is equals to 1 over z t minus 2 z cube t raised by 3. Then what do? We can take this t cube, take that one away. We're having 1 over t minus 2. So if I take 2 as my common factor, suppose I take minus 2 as my common factor here, I'm going to have 1 over t raised by 3 times 1 over minus 2 into 1 minus t over 2, right? If 2 is my common factor here, so minus 2, this will be 1. This will be t over 2, minus plus. Yes, I'll now raise this one up. We are going to have minus 1 over 2t cube into 1 minus t over 2 raised by minus 1. That's minus 1 over 2t raised by 3 special series. This will be 1, everything will be plus t over 2 plus t squared over 2 squared plus t3 over t3 and so on like that. So multiply both sides by divided by 3 raised by 3. So this is minus 1 over 2, 1 over t cube. This will be 1 over 2t squared, 1 over 4, 1 over 4, 1 over 4 and what? 1 over 4t, right? T cube will go. Oh, this is 2 raised by 3. T cube will go. This will be plus 1 over 8 and so on like that. So, and that's our expansion. Now return it back. Recall that t equals to what? T is equals to z plus 2. So finally, f of z is equals to minus 1 over 2, 1 over z plus 2 raised by 3, 1 over 2 z plus 2 raised by 2, 1 over 4 z plus 2 plus 1 over 8. So you can use can generalize, take the sum, and then that is our Laurent series. So this video is brought to you by NAMSSN Unilag 2023-24 ESCO. Thank you for watching. Bye.